Hello everybody, I hope all of you are doing well. Today we are going to be looking at the centroids of composite bodies. Okay, so the aim for today is essentially to familiarize ourselves with the concept of a centroid, and then we will look at an example problem. Okay, alright, so aim is to look at the concept of centroids. Okay, and our focus will be on centroid of composite shapes. Our focus will be on centroids of composite shapes. Which means that we need to first of all define what is meant by a composite shape, right? That's something that we will be doing very soon. Okay, so concept of a centroid is important, and then we'll be looking at composite shapes. Okay, so first of all, what is meant by the centroid? Okay, we will formally define it in the following manner. Centroid is the geometric center of a body or a shape. Okay, so centroid refers to the geometric center of a shape or a body. And typically, if we are on Earth or near the surface of the Earth where acceleration due to gravity is a constant, and if the density of the body is a constant, then a nice thing happens. Okay, so if acceleration due to gravity is a constant, and if the density of the body is a constant, then the centroid is the same as the location of the center of mass and is the same as the location of the center of gravity of the body. Okay, then the location of the centroid is the same as the location of the center of mass, and this is the same as the location of the center of gravity of the body. Okay, so this is a nice thing, a nice consequence of all these approximations. Okay, and these are fairly valid approximations. I mean, close to the surface of the Earth, the acceleration due to gravity can be considered to be a constant, and many of the bodies that we deal with in typical engineering problems, we can assume the density to be a constant. Okay, at least from the point of view of beams and other load-carrying members or structural members. Okay, so from this perspective, we can define the centroid as the following location. Okay, so centroid can be defined as the point on the body or outside the physical shape of the body through which the line of action of the weight of the body passes through. It's a mouthful of words. I'm going to write it down. Okay, so based on the above, so due to the above, due to point number 2, we can define centroid as a point on the body or outside the physical body through which the line of action of the weight of the body passes through. All right. So these are like different ways of defining the centroid, and what is our aim? Okay, our aim is to look at the centroids of two-dimensional composite shapes. Okay, so we come to our aim is to look at centroids of two-dimensional composite shapes. Which behooves that we need to define what is meant by a composite shape. Okay, so first of all, the 2D shapes can be divided into two pieces. Okay, so typical 2D shapes that we are interested in can be divided into simple connected shapes and composite shapes. What are simple connected shapes? These are the basic building blocks. These are the simplest possible shapes that we know geometrically. Okay, so the simplest possible shapes that we know geometrically. Okay, and these are the basic building blocks. Okay, the composite shapes are made up of simple connected shapes, as I'm just going to write it down. Okay, so let me first underline this because this is the main example. So they're the basic building blocks to obtain composite shapes. Okay, what are examples of simple connected shapes? I can have a rectangle. Okay, then another example is a circle. And when I say simple, it has a connected shape, it's not an open shape. Okay, then the third one is a triangle. Okay, of these three, due to our limitations in this particular course, we will be fixing or focusing mostly on rectangular simple shapes. Okay, so if I take a rectangular shape, right, for example, if I draw a rectangle here, okay, then it is very obvious that the centroid or the center of mass of this rectangle is going to be right at its center. Okay, so this is typically specified as C. Okay, so this is going to be the location of the centroid. Okay, and you would have seen this idea used for triangular shapes as well, right, when we had distributed loading. So for example, if I have a right triangle, then it can be shown by integration, that we will not be doing it, of course, due to limitations in time. It can be shown by integration that this is the centroid location, and this centroid location is defined as the following. Okay, in this case, it is going to be 2/3 of the base of the triangle. Okay, and the height is 1/3 of the, or the location height wise is 1/3 of the total height of the triangle. Okay, and likewise, if you had a rectangular shape, then this would be defined as half the width of the rectangle and half the height of the rectangle. Okay, so this is some b by 2, and of course if you look at it this way, then this is going to be h by 2 here. Okay, h over 2. And circles, obviously, they're just sitting right at the center, so it is equidistant from all points on the circumference of the circle. So we will not be looking at that. So for us, the shape of importance is the rectangular shape, because we're going to be looking at combinations of rectangular shapes to build up composite shapes. So now we come to and I just want to make a very brief note, okay, that we can obtain centroid locations by integration, For us, the focus is limited to composite shapes, so we will not be doing that. Okay, so brief note. Centroid of any shape can be obtained via integration. Okay, our focus, as you will be using in mechanics of materials later on, is limited to composite shapes. Okay, so that's my brief note to say that, okay, we are not going to be doing the integration, but we're going to be doing the other things. Okay, now let me define a composite shape. A composite shape is a combination of two or more simple connected shapes, and as easy as it sounds. Okay, it is a combination of two or more simple connected shapes. Okay, this is the fundamental definition of a composite shape. And one would ask, okay, why do we need to study composite shapes? Okay, so why do we need to study composite shapes? A very quick reason can be made from the fact that if you look at common structural members, for example, beams. Okay, if you look at the cross section of a beam, the cross section of a beam is in the form of a composite shape. Okay, so cross section of common structural beams. Just a quick example. Cross section of a structural beam shows a composite shape. Likewise, cross-section of many load-bearing members will show composite shapes of many such load-bearing members will show a composite shape. Right, so for example, if I draw a beam that has a T section, okay, so it would look probably like this. So let me try to draw it out here. My only hazard is that I have to start drawing straight lines, and usually, as you know, things don't work out in my life if I have to draw straight lines. Okay, so here is an example of a T section. This is not too bad so far. Just going to extend this a little bit here and copy that and bring that down here. Just maybe take this a little here. Okay, and join these two together. Okay, and now I'm going to give it a little bit of a depth here. So far so good. Okay, and of course I'm not going to be drawing the full shape. I'm just looking at a small piece of a T section. Okay, so as you can see, right, the cross section of this beam here, which is typically used in many structural applications. Okay, this is a composite shape. Okay, so the T section is a composite shape. T section beam. Okay, this is a composite shape. Why is it a composite shape? It's made up of two rectangles. Okay. as you can see. And in many railway tracks, you will see I-section beams used because of their advantage in carrying bending stresses. Okay, so I-section beams are very similar to the T-section beams, and these are once again very common structural members that you will come across as you look at mechanics of materials and so on. Okay, and I'm going to write down a few things right after I discuss this. I'm going to copy that and bring that down here. I just want to show you the I sections and the T sections, okay, so that you'll see that there is a certain advantage in what we are trying to do here. And I'm going to extend this, give it a little bit of a depth, and of course extend this as well. Okay, go forth here and go forth here as well. Okay, so I'm not showing the full thing. Okay, so this is an example of an I section. The I section, of course, it need not be symmetric like the way I have drawn. Okay, and but the idea is that this is made up of 3 rectangles in that sense. Okay, so this is an I section beam. Okay, this is made up of 3 rectangles. This is made of 3 rectangles. Okay, now and typically I section beam, you will see this in railway sleepers, okay, railway tracks. One of the main examples of a beam that I can think of, because there used to be a railway track next to my home when I was living in India, so I used to keep looking at these beams, and they had these funny shapes, and for me, I was always thinking, okay, why are they designed this way? And then I came to know, okay, they're good at carrying bending stresses and so on, as I went through more into mechanics and so on, as you'll be seeing as well in mechanics of materials. Okay, so the composite section, the centroid, if I find the centroid of composite shapes, here is the nice thing about it. So the location of the centroid of composite shapes can enable one to, from the point of view of stress analysis, can enable one to distinguish between states of compressive versus tensile stresses. Between states of compressive versus tensile stresses. Okay, so the basic idea is that in statics you will learn how to locate centroids. And in mechanics of materials you'll use the centroid locations in stress analysis. Okay, you will use centroid location during stress analysis. Okay, so this is the reason why we are learning this in statics and also towards the end of statics, so that it remains fresh in your mind as you go to look at strength of materials next semester or next year, or whenever you're going to be doing that. Okay, so this will be useful for analyzing stresses and strains in mechanics of materials. All right, that's the basic idea. Now I just want to outline a procedure for calculating the centroid of composite shapes and then go on to an example. Okay, so procedure to obtain centroid of composite shapes. Okay, first step, divide the composite shape into a minimum number of simple connected shapes. divide composite shape into a minimum number of simple connected shapes. Okay, the key is a minimum number. Okay, you can take a body and then divide it into an infinite number of rectangles or triangles. That is typically what you would like to do in finite element methods and so on. Not an infinite number, but a very large number if necessary. Okay, and that is not what we want to do here. We want to break it into a minimum number of simple connected shapes. I want to give it a different color for the underlined word here. Okay, so minimum number of simple connected shapes. Remember that. The second thing is set up a coordinate frame. Okay, a coordinate frame, and choose the origin carefully. So typically you will set up a Cartesian coordinate frame. Okay, and choose the origin judiciously or carefully. Okay, because it is important that you choose the origin carefully. This is the basis for where you're going to be locating the centroid from. Okay, then write down the centroid location of each of the simple connected shapes from the chosen origin. Okay, write down the location of each of the simple connected shapes from the chosen origin. Okay, so for example, if I look at the ith simple connected shape, okay, then here is what I would be writing it down. The location of its centroid is going to be x bar I, y bar I. Okay, so x bar I is the x location of the centroid of the ith simple shape from the chosen origin, and yi bar, I'm just going to get a little lazy here and then say that okay, this is the y location, okay, of the centroid of the ith simple shape from the chosen origin. Okay, so this is the y location. That is important here. And typically you will have an n number of simple connected shapes. Okay, so we got to do this. So let me just put a bracket around here. Okay, and we got to do this n number of times. For all the I is equal to 1, 2, 3, n simple shapes that the composite shape is made up of. For all the simple connected shapes the composite is made up of. Okay, it doesn't it's going to be a little easier than what I'm writing out here. Okay, so don't be taken aback by all these words that you're saying on here. Okay, then the last step is the following. Then we make use of the formal definition of a centroid of a composite shape. Okay, the centroid of a composite shape is equal or obtained by performing the area weighted average of the centroid of the simple connected shapes. Is the area weighted average of the centroid of its simple connected shapes. Okay, so for example, if you have n number of shapes, of simple connected shapes, I'm sorry, that was not meant to be the case. Sometimes this happens where suddenly my notability disappears, and I'm assuming my last recording is being recovered, so I hope this doesn't affect our all the work that I've been doing so far. Okay, it looks like it's getting done. Okay, all right, fantastic. I'm going to continue from here. Okay, sorry, I'm back again. There was a mild crash there. This goes for the people who look at my notability files. All right, so we do this for n number of times, and I think I wanted to write down the last one. The last statement that I was kind of writing and then it crashed on me was the following. Okay, centroid of a composite shape. Apologies for that again. Centroid of a composite shape is the area weighted average of the centroid of its simple connected shapes. Okay, so for example, if I have n number of simple connected shapes, where n can be any number from 1 to 3. I mean, typically it's going to be 2 or more, okay, but there is no point in using this formula for just one shape, right? It makes no sense, absolutely. And then for each simple connected shape, we know xi bar, yi bar, and ai. Okay, so for each simple shape, and ai is the area of the ith simple shape, okay, is the area of the ith simple shape. Okay, then here is the formula that we will be using. Okay, x bar is defined as the summation. Okay, in a sense, summation is the same as integration, right? So this is a glorification of the integration. Okay, summation from I is equal to 1 to n xi bar multiplied by ai, all of this taken over by the average of the area. Okay, so this is I is equal to 1 to n ai. Okay, and then likewise y bar, and I will write down what x bar and y bar are. Okay, this is going to be summation from I is equal to 1 to n yi bar multiplied by ai, or the average of all of the areas. Okay, this is going to be I is equal to 1 to n ai, and here x bar and y bar is the centroid of the composite shape from the chosen origin. Okay, so location of centroid of composite shape from the origin. Okay, so this is the typical formula that we will be making use of in our problems. Okay, and the best way to understand this is by using it in an example, and that's what I'm going to be doing here after I draw this straight line. All right, couple of snafus taking place, right? I suddenly lost the control of my own iPad here. Okay, hopefully that did not affect us in any way. All right, so here is an example problem. The problem. In this problem, I have an L shape, and I'm going to locate the centroid of this L shape. Okay, so here is the L shape. as I'm going to be drawing here. Okay, okay, so in this L shape, here are the dimensions, and of course I want to make sure that these dimensions are the same on both sides. So I just want to reduce the length of this guy. Okay, all right, so here are the dimensions, starting from here all the way onto there. Okay, that's a length of 100 millimeters, and so is the height. So this is 100 millimeters, and likewise is the height here, starting all the way from here onto the top flange. Okay, this is going to be 100 millimeters as well, and the width here of this flange is 20 millimeters, and likewise here this little fellow is also 20 millimeters. And let me draw these in dotted lines. Okay, and what is our aim? Our aim is to come up with the centroid location of this composite shape. Okay, so locate the centroid of the L shape. Okay, using the area weighted average. Okay, using the area weighted average of its simple shapes. Okay, so in this problem, I'm going to capture this problem here, or let me just take only this one. Okay, here is the L shape. I did not mean to cut it. Okay, all right, so procedure for analysis, right? First thing is I break it into a minimum number of simple connected shapes. Minimum number of simple shapes. Okay, if I do this, then there are a couple of ways in which I can do this. Okay, so I can either do it this way. Now look at this. I'm going to draw both the ways. Need to adjust this. Move this guy a little down here. Okay, so I can either do it this way, where I say, okay, hey, I'm going to complete this by saying, okay, this is a set of two rectangles here. Okay, so this is going to be one rectangle here, as you can see, and then I'm going to have the other rectangle here. Okay, this is one way of doing it, or I can do it this way as well, right? I can say that, okay, hey, draw this straight line, plop down. Okay, and then say, okay, this is the rectangle that I'm going to be looking at, one of them, and then here is the other one. Now, both the ways are completely fine. You can either choose method 1, or you can use shape 1 or shape 2. Okay, so this is shape 1 versus shape 2. Okay, so can break it into simple shapes either way. Okay, so can use either 1 or 2 and then perform the analysis. Okay, the result should be the same. Okay, then I'm going to use shape 1. Okay, so okay, so then I come to a new page. I think that's a good sign of things to come, I hope, without any further crashes. Then here is what I do. Okay, so first of all, set up your simple shapes. So I draw this line here so that this becomes shape 1 and then shape 2. So I'm going to call this as shape 2. Okay, and then I'm going to call this as shape 1. Okay, Then I choose a coordinate frame. Okay, I choose an origin. So what's a good point for an origin? I'm going to choose this point for an origin. Typically, I choose the origin such that all the distances that I obtain are going to be positive distances. Okay, so starting all the way from here, I draw this line. This is going to become my x-axis, and then of course this distance here is going to be my y-axis. Okay, and here is my origin, which I'm going to call as O. Okay, so O is my origin. Okay, I typically choose an origin, and I want to maybe write this down. Let me write this down here. Okay, so I choose an origin such that all the centroid locations of the simple connected shapes will be positive. Okay, such that all the x and y locations of the simple connected shapes, or x and y locations of centroid of the simple shapes will be positive. Okay, so that being said, now based upon this, I'm going to locate the centroid of each of these individual shapes. Okay, where is going to be the centroid of this one? This one is going to have a centroid right down here. Okay, so that's going to be the centroid of this first shape. Let me have it as a filled thing here. So I'm just going to fill it and say, okay, I like the blue color here. So this is the centroid location. I'm going to call that as C2. Okay, then I'm going to call the centroid of the first shape as a C1. I'm going to copy this and I'm going to paste it and bring it down here. Okay, so this is approximately where the center of this shape is. I guess let's say here. Okay, then I'm going to call this as C1. Okay, so C1 and C2 is the centroid of shape 1 and 2 respectively. Okay, so far so good, right? We chose, we draw the figure that we are given, we choose an origin, and then based upon that particular origin, we write the centroid of these individual shapes. Okay, so maybe just to heighten the presence of these things, let me say that, okay, this entire thing is made up of one color here. Okay, as you can see, and the other shape is made up of the other color, that is this guy here. Okay, so these are my two simple connected shapes with the origin chosen and hopefully a straight line drawn and all the shapes marked as well. Okay, beautiful. Then what do? From the origin, okay, I'm going to capture this guy once again. So far so good. I have done all of that necessary. I'm going to bring it down here. Okay, and then I'm going to start writing out some dimensions and so on. Okay, I need some space for that. Okay, so here are the things that I'm going to do. So starting from the origin, I'm going to locate the centroid C1 and call that distance as x1 bar. Okay, so look at this. So from the origin all the way to where this centroid is located, I'm going to call that distance as x1 bar. Okay, then from the origin to where the y location of this creature is, I'm going to call that as y1 bar. Okay, exact same idea. Okay, so this is supposed to be straight, so I think this is straight now, or approximately straight. Okay, okay, almost there, bear with me. Okay, that's good enough. And I'm going to call this location here as y1 bar, always taking it from the origin. So I guess in that sense my arrows will be unidirectional, right, starting from the origin. Okay, so this is going to be y1 bar, and I do the same thing, and let me draw these as dotted lines before I forget. All of them are supposed to be dotted lines, okay, because I'm looking at distances and so on. Okay, and I do the same thing for the other centroid. Okay, so starting from the origin, likewise. Okay, I know that that is a line that extends from the origin, so maybe let me do the following. Okay, so this is x1 bar here. I'm going to take this line and then bring it down here, and then I'm going to draw a line directly all the way to here, and that's going to be x2 bar for me. Okay, so that's going to be x2 bar, and likewise I'm going to have y2 bar as well. So starting from here all the way on to this guy here is going to be y2 bar. I'm going to make sure that these are straight, or as straight as they can be. Sometimes they give me trouble. Okay, so that is going to be y2 bar. And dotted lines, of course. Bear with me, we are almost done. Okay, that is beautiful. So all of these have been marked, and then I also know the dimensions of this entire body, right? For me, what are the dimensions? The total height starting from the origin all the way to the top flange was 100. The thickness was 20. So here is the thing that I'm going to be writing down. So from here, let me write down the dimensions and so on. So this guy is going to be 20 millimeters. Okay, the thickness of that bottom flange, that's called as a flange. And then all the way starting from here on to here. Okay, so let me draw these lines so that, and let me take this guy, extend it all the way on to here. Okay, and this height here is going to be 100 minus 20, so that's going to be 80 millimeters. Right, and then I also have the other one which I can draw down here. So before that, I'm going to draw these as dotted lines. Okay, they signify the dimensions that I was given, and starting from here I also have the other dimensions. Okay, so from here on to here, as you can see, that's going to be 20 millimeters as well, the thickness of that, and all the way down to here, that's going to be 80 millimeters. Okay, so in that sense, this is 20 and the rest is 80. It's a nice uniform problem. Sometimes the numbers don't have this sense of uniformity. Typically during exams, they will not have be the case that way. Okay, so I'm just going to draw these as dotted lines. Okay, and this is going to be 80 millimeters. And let me scoot this entire figure a little down from the text block that I have written down there. Okay, and this is 20, and this is 80 millimeters. Okay, so once I have all of this, then it is just a question of writing down what are the areas and so on. Okay, so the area of the first piece is going to be 20 multiplied by 80. Okay, this is fairly straightforward. Area of the second piece is going to be 100 multiplied by 20. So that is important. Okay, so let's look at the first piece. Okay, I'm going to copy this figure and bring it down to the next page so that we have it in front of us. And maybe I'll shrink the size of this figure as well a little bit as I'm writing down all the details from this. Okay, so I'm going to copy this and bring it down here. Let me shrink the size, and then let's start writing down all the details. Okay, so for shape 1, the area of the first shape is going to be 20 mm by 80 mm. Okay, then the x1 bar, what is the value of x1 bar? This is going to be 20 divided by 2, right? So this is 20 divided by 2, which is 10 millimeters. Y1 bar is going to be what? Y1 bar is going to be 20 millimeters plus half of 80. Okay, so this is going to be 20 plus 80 by 2. Okay, so this is going to be 60 millimeters. This is important to know. Okay, then the second thing is area of A2 is going to be just 20 by 100. Okay, this is the area. Then x2 bar is also fairly straightforward. As you can see, this is just half of 100. Okay, so this is 100 divided by 2, which is going to be 50 millimeters. And y2 bar is going to be half of 20, so 20 by 2, which is 10 millimeters. Once I have all of this, then I write the generic formula. X bar is going to be, because I have only two pieces, right? This is going to be x1 bar A1 plus x2 bar A2 divided by A1 plus A2. I'm just using the generic formula that we had from earlier, okay? And then y bar is going to be y1 bar A1, y2 bar A2, all of it divided by A1 plus A2. I have all the values that have been calculated there, so all I have to do is just do the substitution, okay? So here I'm going to say, okay, x bar is now going to be x1 bar, which I had calculated earlier as 10. So this is 10 times the area of the first piece, which is 20 times 80. Then I'm going to have the second one, which is x2 bar, which I had calculated as 50 millimeters, as you can see. This is 50 times the area of the second piece, which is 20 times 100. All of this will be divided by the total area of the two pieces, okay, which is 20 times 80 plus 20 times 100. Okay, substitute and then solve, and you'll end up with 32.2 millimeters. Okay, look at the dimensions. Okay, because there's a location, it has to be in the dimensions of length. Okay, and here we are using millimeters, and then y bar is going to be the following. Likewise, the same idea, y1 bar, which was 60 millimeters for me. So this was 60 multiplied by the area of the first piece, and then the second one was y2 bar is 10 millimeters, as you can see, 10 times 20 times 100. All of this will be divided by the total denominator, which is 20 times 80 and 20 times 100, and all of this computed together is going to give me, what do you know, 32.2 again. Okay, so this x bar and y bar now is now the location of the centroid of the composite shape. Very importantly, from chosen origin. Okay, this is an important line here. Okay, because if you choose a different origin, then your numbers are going to be different, but the location is still going to be the same. Okay, so if I were to do this following, if I were to show this, this is what is going to end up being the case. I'm going to grab my figure from above. I think I should still be able to copy and paste if I remember right. Yeah, beautiful. Okay, so we can still do that. I'm going to get rid of some of these distractions here because we are done with all these dimensions and so on. Okay, cut that off. All right, so this is the main figure. This is the origin that I have chosen. Okay, so in this situation, the centroid of the actual body is going to be somewhere here. Okay, I'm going to copy this. It's going to be a little less than x2 bar and a little less than y2 bar, so it's going to be somewhere here. Okay, so probably here. And let me give it a different fill color, make it a little brighter for you. Okay, so this is probably going to be the location of the centroid of the main shape. Okay, and if I were to mark this, then here is what I would do. I'm going to take all of these guys and bring it down here so that I can now say, okay, starting from here all the way to where my origin was previously drawn is now going to be y bar. Okay, and starting from my origin, which was right here, all the way to where this point is located is going to be my x bar. Okay, for the sake of convenience, I'll bring this guy down here. Okay, so this is now going to be x bar. And of course, I do prefer to use unidirectional arrows as I can draw them because these are defined from the particular origin that I have chosen here. Okay, and this x bar and y bar, this is the centroid C of the entire composite shape, and you can write this as 32.2 mm 32.2 mm, where this refers to the x bar location and this refers to the y bar location. All right. And we will see in the later problem, we're going to make use of the same problem in looking at moment of inertia calculations, which is going to be the next concept talk that we're going to be having. Okay. All right. So this is the end of the problem, and I want to just very briefly go through what we have done here. Okay. First idea is, okay, I'm given a centroid, I'm given a composite shape, find its centroid. What's a composite shape? It's a combination of two or more simple connected shapes. Why do I need to study that? Is because many structural members have cross sections that are composites, and structural members are used for load bearing capacities, and it's important for us to design them. So they also help us in analyzing the state of stress and strain in these physical structures, okay, in the material. Okay, so I have this composite shape. How do I find the centroid? I first break it into a minimum number of simple connected shapes, either one way or the other way. It does not matter whether you choose one or two. Once I choose either one of them, then the important thing is I'm going to set up an origin. I set up an origin O typically such that all the dimensions that I get will be positive. Sometimes it is not possible in certain problems. You may be forced to choose an origin that is more convenient. Okay, so choose it at your convenience. Okay, so I just want to mention that point. Choose at your convenience. Okay, and then once you do that, each of these simple shapes, you locate the centroids of those shapes C1 and C2, and we did that. We dimensioned all of this. We looked at x1 bar, y1 bar, x2 bar, y2 bar. We write down the values of each of them based upon how we have built this shape, and then we make use of the generic formula, okay, which is this x1 bar a1 plus x2 bar a2 by a1 plus a2, the area weighted formula. Okay, I just want to put a block around this formula here. Okay, this is the key formula. Because we have only two shapes, we're using it 2 times. Okay, typically you can use it as many number of times as you want. Okay, if you have 3 shapes, then you can use it 3 times. Okay, so for example, if we had 3 simple shapes, right, the formula would be x bar is x1 bar a1, x2 bar a2, x3 bar a3 divided by a1 plus a2 plus a3. Okay, and likewise y bar would be, this is the numerator, y1 bar a1, y2 bar a2, y3 bar a3, and all of it divided by a1 plus a2 plus a3. Okay, I typically want to write this out because sometimes I get a question, okay, what if you have more than 2 shapes? Then I just say, okay, add one more term. No big deal. Okay, so this is if I had 3 simple shapes and so on. Okay, and once I obtain the answers by substitution, I just mark the centroid of the entire composite shape this way. All right, so we're going to end the lecture here, and I hope all of you are staying safe. I'll see you again in the next lecture. Okay, thank you very much and take care. Bye bye.